Nine. Good afternoon, everyone. Let's wait just 1 minute more for people to join. We are already 41 attendees. And then we start this webinar organized by ETIP SNET and especially the working group 3 on flexible generation. Okay, we can start. So I introduce myself. I'm Maria Laura Trefiletti. I'm the ETIP SNET coordinator, and we would like to welcome to this webinar organized by ETIP SNET and especially the working group 3 in flexible generation. Here I would like to welcome also the speakers, Alexander Widerman, that is the chair of the working group 3, and Christian Bergins, Georgos Christoforidis, and Peter Stetner, that will be the speakers for our webinar today. I want just to give you some instruction for the logistic and especially for the questions. So you will see the picture of the video of all the speakers, and you are automatically muted by the system, but you can write your questions in the session dedicated to this. And after, so the webinar will be divided in 3 subsections. 2 topics per speakers, and after each of this subsession we will open the floor for questions, and I will read the one that you wrote in the dedicated question session in your board on GoToWebinar. So please don't hesitate to write your question, and it will be read immediately after the finish of the 3 subsessions. So now I will leave the floor to Alexander Widerman for the welcoming and for the first part and starting our webinar. Thank you very much. So Alexander, the floor is yours.
Yeah, thanks a lot, Maria, for this kind introduction. Good afternoon, ladies and gentlemen. It is a great pleasure to welcome you to this webinar of the Working Group 3 titled Flexible Generation in a Low Carbon Renewable Energy Sources Dominated Energy System. This is the 3rd webinar in the row of 3, which has taken place at the end of this month. So there was a webinar last Monday on storage by the Working Group 2, and another webinar also on Wednesday on sector coupling and smart grids. And this is the 3rd one, which will conclude so the series of our webinars. Well, the ETIP SNET vision is the basis for defining the specifications for further research and innovation needs in the transition from today towards Europe's energy systems of the future. And what you will listen to in this webinar is just as the status of the state of the art right now. So we are 27 member states in Europe, and each of these member states, of course, have very different energy mixes. And we have to encounter this, we have to take this into account when we are talking about the transition towards a decarbonized Europe in the near future. And also we have to think about which is the fastest way of how to go ahead. But we have also in our group Flexible Generation evaluated all energy sources and all plants and energy conversion systems with regard to the dispatchability. So that means to deliver power on demand for those times where so the renewables are not available because sun is not shining or wind is not blowing. And we are of course, we think that the decarbonized Europe can be only achieved if we have a very high share of renewables. And this, of course, means that we have to increase our storage capacities in the future, and we have to directly integrate them, of course, with the conversion systems. We also have to take into account that the electrification of all sectors, also including the mobility sectors, means that we will have a vast amount of electricity generation and power generation in the future, and we have to also think about the role of each of the conversion and the generation techniques in the transitional period, but also in the future period. And we also see that so-called conventional plants, thermal plants, will of course have their place in the future, and maybe also driven with green fuels. And we will also give an outlook how the future would look like. I would like to mention that we have about 35 members in our working group, and in order to get inputs from every aspect, we formed a task force of 11 members who gave their inputs, who discussed with us about the contents of these contribution, so that we do not focus on one special kind of energy conversion techniques, but we want to cover everything, and we want to discuss also all the shortcomings and all the advantages, disadvantages, in particular with respect to their role in the future energy mix. And at this point, I would like to thank everybody for his input. Today we have three distinguished speakers who are also specialists in various fields. So we have as the first speaker Peter Stetner from Andritz Hydro. Peter is the head of market strategy, and he is also defining research and development agendas. He will present the first two chapters of this webinar. This chapter 3 and 4 will be presented by Professor Georgios Christoforidis of the University of Western Macedonia, and he is a specialist also in the inclusion, in the integration of renewable energy sources into the energy system. And the final two chapters will be presented by Dr. Christian Bergens, who is strategic market manager and expert of Mitsubishi Hitachi Power Systems. So I will just pass over to the first speaker. Please start your presentation, Peter.
So, thank you, Alexander. Good afternoon, everybody, also from my side now. My name is Peter Stetner. I'm working within the hydropower industry for more than 25 years now. But my role today is not to make any advertisements on hydropower, but I will give you a short introduction into ETIP SNET, and afterwards also a few words on where we are standing today in Europe. So, transition does not work. Okay, now it works. A couple of years ago, a rather fragmented community in Europe, dealing with all these grids and smart grids and storage issues, convened and formed a European technology and innovation platform for smart energy networks for energy transition, short ETIP SNET. Which addresses in a consolidated form now the innovation challenges which are related to the transition of our energy system in order to make it resilient and in order to achieve. Oh, I did nothing. So this hopped over, but I didn't do anything. So did I lose control here?
Yes, I will. Sorry, I will try it again. So, okay, please try again, Peter.
Yes. So I see my mouse, but yeah, I'm back here. Okay. In order to address all the issues necessary in the evolution towards a carbon-free system, and of course this goes far beyond smart electricity grids only. So what's our mission? Yeah, we shall set out a vision for research, development, and innovation for a smart network for the energy transition. And this means also to engage all in relevant stakeholders. We prepare and update, of course, a strategic research and innovation roadmap in a consolidated manner. We report on the implementation of specific research and development activities, both on a European and also national and regional level, and of course also on an industrial level. Important, we provide input to the Strategic Energy Technology Plan Action 4. This Action 4 addresses the technical challenges raised by this transformation of our energy system. But we identify also the innovation barriers, and this is mostly about non-technical issue. This is about regulation and financing. And we form an enhanced mechanism for knowledge sharing about the whole industry, and in order to bring the results to the communities. We prepare consolidated, and this is essential, stakeholder reviews as an input to the European Commission and also other policy initiatives and policymakers. How does this work? Yeah, as mentioned, this was triggered by the European Commission, and at that time a consortium was formed, yeah, with around Sabala, yeah, and on the top, a governing board is the leading body of this ETIP SNET, and out of that, 9 members form the executive committee. The many experts are convened in 5 working groups, but they're permanent working groups, but there's also a stakeholder coordination group covering ministry representatives, funding agencies, national platforms, and regulators, for example. So these are the 5 groups dealing with storage technologies, dealing with the grid as such, dealing with flexible generation. This is our working group 3. But last not least, important also digitalization and how the innovation is implemented in the business environment. So all today's speakers are members of the flexible generation group. The basis of our work is written in a Vision 2050, which was established a few years ago and published in July 2018. You see also the download links here. And recently, the Working Group 3 published a white paper, how the flexible power generation in a decarbonized Europe can work together with the whole system. And last not least, every 2 years, the so-called implementation plan is updated. And recently, the implementation plan 21 to 24 was published, where the specific research and innovation activities are listed and described. Flexibilization of the energy sector. What does this mean? If you look on the power system only, it's quite clear that generation and the flexibility of the generation system plays a major role, but it's also about storage and what storage has to play in the system. And energy is not only about power, but sector coupling will more and more play a major role when it comes to power to heat, power to gas, and so on and so on. We will hear about these issues also today. So where are we today in Europe? Let's have a look on the world first. And we come now to electricity. If you see, if you have a look on the stated policy scenario of the IEA, this reflects the impact of the existing policy framework and also already announced policy intentions. And there you see today in the global electricity generation mix, we find around one quarter renewables. This will increase to 37 and 44% by 2040. What does this mean? This stated policy scenario, and we are on this track today, is neither sustainable nor able to fulfill the Paris climate targets. So what about Europe? If you look on Europe, you find a different pictures. First, you will see we have a higher share of renewables already. We had a decrease in electricity generation, which is good, means efficiency is increasing, but you see also by 2030 and 2040, electricity generation will increase. Why? We will hear about later. 1/3 renewables, more than half renewables, and 2/3 renewables by 2040. Looks nice, but even in Europe, this scenario would not be enough. We have to enhance and we have to speed up. This is not ambitious enough. So this was power, this was electricity only, but the target is to reduce the overall greenhouse gas emissions, the net emissions, to 0 by 2050. Only the yellow is electricity. All the other reductions have to come from other sectors, and you find even negative emissions. These will come from carbon removal technologies, carbon capture and storage, carbon capture and utilization, and also, and this is the green, from land use change, and forestry. These are carbon sinks. Back to energy. Where do we have to decarbonize? If you look on the today's electricity mix in the EU, you find around 21% only from renewables. Decarbonization means we need first an increase of renewables in the power generation mix. But if you look where the primary energy goes, you see also only 25% of the total energy consumption today is in form of electricity. And if you see transportation, even more than 90% is fossils. Also in the industry, half is from fossils. Means we need electrification. Therefore, in future in Europe, we will have more electricity generation than today. Society has to be electrified, and the fossil fuels have to be substituted by synthetic fuels, biofuels, hydrogen in all sectors. We will hear about later on. Generation. Now, storage. This is the situation of bulk energy storage today. It means utility scale. And you see on the very first view, globally, it's totally dominated by pump storage today. More than 94% of capacity and even 99% of energy stored is with pump storage today. Only a small rest is electrochemical and thermal, and of course this has to change. And the situation in the EU is more or less the same. So that's for the moment from my side. If there is any questions, we would try to answer it now. The one or other will be, of course, answered also later on. Thank you.
Yeah, so thank you, Peter. I see here a question. So is the use of hydrogen in fuel cells also considered as electrification? It's done by Louise Gilles. Yeah, Louise Gilles.
So I'm not sure whether I got it. I got your question acoustically.
Yes, the question is the use of hydrogen in fuel cells also considered as electrifications?
No, first of all, the hydrogen has to be produced. I don't see the hydrogen as in this case as primary energy carrier, but perhaps you have other views on that, Georgios and Christian.
We will hear, I think, later about hydrogen use, and for me it's a matter of definition if that is electrification, because the primary energy in future will be anyhow green electricity.
That means the hydrogen produced and afterwards burned for electricity generation shall be seen as an intermediate energy carrier, but no more as an primary energy.
Okay, so
if I can say something about this. I think this question was a little bit too early, because the third part of our contribution we tackle so this way of just also green fuels and utilization of green fuels in various sectors, not only for electrification. So I think this is a good question which we should discuss after listening to all the presentation.
Okay, so there is another question from Luis Gil. Does the scenarios include the possibility of less economic activities and so less energy consumption?
Yes, of course, yeah. There's always 3 scenarios which are published by the IEA. The one is as what I presented was the stated policy scenario. That means also the ambitions are included in this scenario. Then is the business as usual scenario. This is the most conservative one. And there is also, they call it today, the sustainable development scenario. In each scenario, consumption reductions are already included. This is all based on macroeconomic development, yeah, and out of that, the consequences to the energy systems are published. Yeah, of course, reduction is always included. Reduction by efficiency, by less macroeconomic growth, etc., etc.
Thank you, Peter. The last question is from Coralie Badajoz. Is what LULUSF mean? Is about an acronym that probably you use in using the presentation.
I think I mentioned it. This is land use change, and forestry. Yeah, means also humus and stuff like that. Yeah, all change in agriculture and in forestry is here included or considered. Land use change, and forestry.
Thank you, Peter. Okay, there are no other questions for this sub-session, so I would like to thank you, Peter, and then leave the floor to Georgos Christoforidis for the second sub.
Yes, so
I want to just remind everyone that all the attendees that there will be also a question and answer session in general at the end of the presentation, so you can still have time to address your question to the speakers. Thanks. Okay,
Georgos, the floor is yours. Now we are listening to integration aspects and also storage requirements.
Thank you, Maria. Thank you, Alexander. Good afternoon, everyone. Thanks for being here. I continue in this webinar. Oops, it was a little bit too early with section 3. Actually taking the floor from Peter that explained the current situation. And we saw that, especially regarding electricity generation, the current situation in Europe is bound to change drastically. Everyone's talking about energy transition. And based on the evolving EU policy framework, we do expect, first of all, a gradual phase out of the coal power plants and a significant reduction in the shares of natural gas and nuclear energy. And at the same time, of course, we expect a significant increase in renewable energy generation. This means that most probably we are talking about variable renewables and especially PV and wind energy. All the above are enhanced by the policy targets, both of the EU, both for 2030 and the long-term strategy for 2050 to become climate neutral or to have net zero emissions. And we do expect more than 80% of electricity coming from renewables in 2050. Which are the primary energy sources for power and heat for the future? How will we cover the energy demand then? One obvious answer is that we can do that partly with the increased deployment of wind and PV generation, with high potential for large-scale deployment at terawatt scale of power. As for example, notable examples are rooftop PVs and offshore wind energy. But again, at the same time, they are variable and intermittent. And with we have even today difficulties to have accurate generation forecasts over time. Then we expect biomass to play a role as well, with its main advantage being its excellent storability. But there are issues, well-known issues about its limited resources. And moving on with another category with significant generation potential in the scale of multiple gigawatts. In this category, we have put run-of-river hydro plants and geothermal and biogas plants. All these can cover part of the base load, but with limited storage capabilities. On the other hand, if storage capability is considered mainly, the main technologies or sources with reasonable potential, even up to terawatt hours of energy scale of generating energy, are hydro dams or reservoirs, pumped hydro, and solar thermal. These are the main technologies capable of providing storage capacities at very large scale, but they have topology and geography restrictions. This means that it's not for everyone. It may be site-specific. Then nuclear and up to a point, very limited coal and gas plants will still be here, though especially nuclear power plants only in certain countries and significantly reduced. Finally, other technologies like wave or tidal power again are largely regional and not really mature yet, having to overcome also environmental restrictions, while waste-to-energy power generation must run continuously and also face some strict environmental permit procedures. This is just a picture of how the mosaic of the energy sources will look according to our view in working group 3. Now, if we let's see and remember how a high percentage of variable renewables is changing the average system load of an electricity system. And if we take another example, the example of Greece, and this is actually the average system load of last August 2019. If we take from this one the average wind generation of that month and the average PV generation, actually here, if we take different days in between days of the same month, it will not be so, let's say, smooth. But again, if we subtract these two profiles from the average system load, we get the so-called residual load, which should be covered, and this is the important point, by other dispatchable generation plants. because we consider that by themselves PV and wind are not dispatchable. Since though we expect a very high increase of VRES, of variable renewables, the profile of the residual load needed to be covered by the rest of generation changes drastically. And as we add more and more, we come into a situation where the rest of generation needed to be taken on and off more rapidly and frequently, increasing the needed ramp up and ramp down rates by them. And at the same time, the base load is considerably reduced, and this means that must-run plants or non-flexible ones will be more difficult to treat by the system operator. And even at really very high VRES penetration, we can expect negative residual loads, which actually means that we either have to curtail power generation from renewables or to have large storage capacity to store and use later. And this is, of course, the well-known DAC curve. Now, even today, we can see that in several countries in the EU, variable renewables have a percentage in annual electricity generation quite high enough, ranging from 15% in Italy to even more than 60% in Denmark. And while for percentages up to roughly 30% of variable renewables, they just influence the operation pattern of the system, there are cases, most notably for Ireland and Denmark, where VRES covers almost all generation for some periods. And this actually shows the what is the current situation, what is to be expected in the following years. Now, this brings us to the question that is largely related to the field of our working group 3. What flexibility needs do we expect in Europe the following period? Actually, the TSO Association, the Transmission Systems Operator Association in Europe, the NSOE, they have a regular publication called MAF, Midterm Adequacy Forecast. They have estimated the flexibility needs of the European power systems in 2025 in terms of peak upward and downward ramps. And to be precise, this figure that you're seeing in the slide shows the hourly residual load ramps. That is the hourly changes in load minus variable renewables, again, generation, that are requested from dispatchable generation units when considering each market node independently. You can, it's a little bit small letters, but each country independently, more or less. However, because the European transmission system is interconnected, this can create benefits from the spatial aggregation through balancing in load and variable renewable generation. For example, if we consider two interconnected countries, there is a high chance that these two countries do not face the most critical ramps at the same exact time. If we consider this, we result in approximately 30% reduced estimation of the peak residual demand. And this actually showcases the importance of having a large interconnected power system in Europe and why we want to enhance the interconnections. Now, because we're discussing about flexibility, I think it's important to clearly define two important aspects. First of all, operational flexibility refers to the capability of a generation plant to support the system fast and reliable, and hence the operational word here. This is actually what is implied in the previous slide when we refer to flexibility. The white paper of our working group discusses a lot about these concepts, and we have realized that over the last decade, the operational flexibility has improved for both thermal and hydro plants. The minimum loading of generation has been reduced, as well as the starting times, while the ramping capabilities have increased. Furthermore, operational flexibility implies the capability for black start, and this is actually the process of restoring a generation plant to operation without having to rely on external electric power network to recover from a total or partial shutdown. The main challenges are material stress and wear due to cycling, and the increase of efficiency, especially when operating under park load. Second, we also have fuel flexibility, and this refers to generators being able to operate with different fuels or a mixture of fuels. And this is particularly important in the ongoing discussion about how to treat phasing out of coal-fired power plants, where the option to operate under different fuels or mixtures is on the table. And here the main challenge is to include hydrogen and to mix different fuels at various qualities. For example, natural gas and hydrogen mix. Now, we had a long discussion in our working group about the operational flexibility characteristics of power generation technologies, and we have come up with an adapted graph that you see here, categorizing several types of generation according to their flexibility characteristics. This graph compares the main power generation technologies upon 3 flexibility characteristics, and these are minimum load at the x-axis as percentage of full load, ramping rate capability in the y-axis, again as percentage of full load achieved per minute, and finally the hot startup time that is shown in the size of the bubble. We can see, because there's a lot of information inside, that, for example, modern gas engine power plants operated especially in multi-units, possibly with fuel flexibility as well, have excellent flexibility characteristics, but again with relatively low efficiency, probably below 50%, while hydro, reservoir, and pump storage have very good flexibility characteristics with higher efficiency. I think that we can also see why nuclear and coal or lignite power plants are operated as base power plants with very limited flexibility characteristics. Now, in our recent white paper that you can download, you can find download links in the first slides of this presentation, we have evaluated in a qualitative manner the main energy sources with regard to their flexibility characteristics, both in terms of fuel flexibility and load or operational flexibility. Without going deep into details, you can see that, for example, regarding fuel cells, the PEM fuel cells have very good operational flexibility characteristics, but limited fuel flexibility ones. On the other hand, SOFC have poor flexibility characteristics, but higher fuel flexibility. Gas turbines and reciprocating engines both have good fuel and operational flexibility, while hydro turbines are characterized by good operational flexibility characteristics. The thermal power plants can be fuel flexible, but in terms of load flexibility characteristics, they suffer apart from the ability to provide frequency support. Finally, as I said before, solar and wind energy are not flexible power sources, at least without being coupled with storage or other flexible generation units. This brings us to the connection with the next section that we are discussing about storage, and mainly I would say about long-term energy storage. We can, apart from the fact that we do expect an increase variable renewables, mainly PV and wind, and we saw how this affects the system load and changes the residual load needed to be covered by other flexible generation. This situation is fueled as well by the fact that generally the produced power from wind and PV do not coincide with electricity demand. This is a well-known feature, but again plays an important role specifically for power systems. Here we discuss a study even from 2012 depicting the situation in Germany, and it was even then that we saw that the residual load with increased PV and wind penetrations does strange things, let's say, to the power system. For example, if we take the most aggressive option here, that is try and install 6 times more power from wind and PV as it was then, we have almost 2,000 hours or a little bit more when surplus power from variable renewables are to be expected. And we have to do something with that. For another, on the other side, for another 5,000 to 6,000 hours of a year, we have a residual load that should be covered by flexible and dispatchable generation with characteristics like the one we saw before. Now, if we can have, let's say, bulk energy storage options, we could potentially use it to shift part of the surplus power to cover the residual loads. And this means that we need to think about how thousands of terawatt hours can be stored seasonally and then use it at a later stage when needed. Now, generally, storage can have multiple uses in a power system. And this depends on the power and energy capacities and the response time of each technology. Storage can enhance the stability of the power system by providing high power outputs at short times. It can also smooth a variable renewable power generation profile during a day or parts of a day, providing the so-called capacity firming. On a daily basis and providing sufficient energy capacity is available, storage can also help to shift loads at certain times of the day, filling valleys of the profile or reducing peaks. And as was explained previously, at long term, storage can act as an energy reserve, obviously as long as large storage capacities exist. We will not go deeper into the effects of storage into power systems, as this was dealt with by Working Group 2 and the webinar of last week. Speaking of large-scale electricity storage, the main options are still hydro dams, with the notable example of Lake Largescale, with a capacity of nominal capacity of 7.8 terawatt hours. This actually would be enough to cover the whole annual electricity consumption of Latvia and leave something for something else. also. Pumped hydro can store electricity at gigawatt or gigawatt hour scale, providing significant services to the power system. The capacity of pumped hydro in Europe is currently around 50 gigawatts and has generated more than 32 terawatt hours in 2018. But the potential is considerably higher, could be more than 1,000 terawatt hours, and with high efficiency up to 85%. As I said before, both of these are relatively difficult to build and can be installed only at favorable places. Concentrated solar power plants can offer also large-scale electricity storage at hundreds of megawatts or megawatt hours scale, with a main example in Europe being a CSP plant in Spain with a total of 150 megawatts in 3 units and the capacity of more than 1,000 megawatt hours annually. Also, battery storage systems are slowly entering the large-scale storage options as centralized storage, with plants in operation at hundreds of megawatt or megawatt hour scale, and plants currently in construction of around 100 megawatts or even more. And obviously, decentralized storage can play a role as well, especially if they can be under an aggregator and, of course, provided that they reach such levels of overall capacity. Some other technologies that with which we can achieve large-scale electricity storage is LAES and CAES, or liquid air energy storage and compressed air energy storage. Liquid air energy storage refers to a technology that uses liquefied air or nitrogen as storage medium and belongs generally to cryogenic energy storage. They can be combined with gas turbine peaking plants to increase overall efficiency. On the other hand, compressed energy storage is another way to store energy, particularly from variable renewables, again. And both of these technologies can provide storage at hundreds of megawatt scales and gigawatt hours of storage, and have an efficiency of 50 to 60% and fuel efficiency up to 90%. Then we have also another technology that is high temperature heat storage, where mostly electricity storage is combined again with fuel-based peaking plants. Such plants use solid materials or salt heat for storage, and they have an efficiency of around 40 to 45%. These are, let's say, the portfolio of large-scale electricity storage options that we currently have. And this means that we do not discuss here other types of storage that mostly are used for have smaller capacities. Now, there are several studies, numerous studies and analysis about the applications for certain energy storage technologies. This graph that you're seeing tries to categorize some of the available storage technologies in terms of their storage capacity and time period of use. As explained before, with a very high VRES share, the need for storage increases significantly, and it can be estimated for Germany again that the amount of storage needed is by a factor of 1,000 higher than the existing pumped storage capacity. And this brings into focus sector coupling. You can see that in the graph is power to gas and hydrogen, and this is capable of seasonal storage at large quantities, at least when pumped hydro and hydro dams are impossible to build in a certain region. Okay, And this brings us to the ETIP SNET vision for the integrated energy networks of the future, where storage interacts with relatively all sectors. And it is really sector coupling that will act as a final enabler when more and more PV and wind power will be installed, in order to be able to use the generated energy from VS even when it will surpass the amount of energy that can be used in the electrical power system as seasonal storage. So, for example, we could use the high amount of excess energy to produce fuels for the transport industry, to transform the heat for the heat networks, to gas for the gas networks, and so on. And now, yes, I will pass the floor to Christian Bergins, unless there are some questions for these two sections. Thank you very much. Maria, we're not, I cannot listen to you.
Yeah, you are mute.
Okay, sorry. Can you hear me?
Yes, now.
Yeah.
Yes.
Okay. So I was saying that there are several questions, and some of them are really long as well. So maybe Georgios, if you want to open the box, but in any case, I will read them for all the audience. So I was also thanking you for your intervention, but I was mute. Okay, so let's go with the first one as appear on my screen. It's done from Mark Howitt. So a key operational flexibility characteristics that is ignored is seasonability. The monthly generation profiles of wind and solar are the mirror image of each other. This means that with the right proportion of each, seasonal storage is not needed. All that is required is the longest low generation period, equal Hector-Dunkel float, plus a bit for follow-on patterns before storage has recovered. So this is a comment, but I don't know if you want to react to this comment.
Actually, I'm not sure where I can see the exact question because it's a long one, and I'm not sure if I have understood well the question.
Normally, it's more, yeah, it is a statement, let's say, but I copy and paste on the chat for all of you. So maybe in the chat you are able to see. Let me try. Voilà. So this is the question as I read. Yeah. So now you are able to read and you can.
Well, yes, this is a big story, okay, and it's from which perspective you are looking at it. What we did here is to try and categorize the characteristics of the operational flexibility in terms of the three options, as I said, of the three parameters. Indeed, there are times when wind and solar complement each other. On the other hand, the problem of not accurate forecast is also an important one. I don't mean to disagree actually, but this was not in our intention to go that deep into, let's say, things that have to do with the power system side, at least for the moment. And thank you for the question. I think it's quite interesting, and we can discuss it for a long time. Fortunately, we don't have really much time today for that.
Thank you, Georgios. This is another question, always from Mark, another statement. So you can read on the chart as well. So adiabatic KS is 70%, and that's cheaper than undated gas-fired peaker plants or batteries of equivalent size.
This again brings into the discussion the cost parameter. This is something that we deliberately didn't include in the white paper. One reason is that cost parameters need very careful study before. For example, when dealing with LCOE, especially for PV and wind, things change very rapidly, and something that you do after even some months can become obsolete. And it was a deliberate decision of the working group to leave out the cost parameter. So yes, at points it can be true, but this was not something that we included in this presentation or the white paper.
Okay, thank you. So then we have another question from Luis Gil. So I copy and paste also this, and I read it. Voila. So this is the question is, and CO2 to methanol, is this interesting for flexible electricity generations?
I think that maybe Christian deals with that in the next two sections of the presentation. Again, I would say this is a matter of perspective. If you ask me, yes, it is interesting, but it has also to do with what we want from flexible electricity generation. We're talking here about the sector coupling. Okay, so yes, it could be interesting, but I think that Christian is more capable of answering this question better than myself.
Okay. Then we have another question from Mario Bruno Ferreira. So peak ramp into ENTSO-E math graph are hourly?
Well, yes. The MAF refers to the, and I'm looking to my notes here, to the hourly residual load ramps, the hourly changes in load, okay, minus variable renewables. So yes, this is true.
Thank you. Here there is another question slash statement from Mark Howitt. Again, it's long, so I will read, but I will ask also you read together with me. So the power to gas is currently below 30% efficient. Thermodynamic maximum is under 40%, with plant costs far more expensive than 70% efficient gas. So the role of hydrogen is where something else is wanted from it. For example, mobility, fuel cells, injection into gas grids, industrial processes, chemical formation of other fuels such as for aviation.
Oh yes, I do not really disagree with that. Again, sector coupling is hinted here. So we can produce hydrogen from excess variable renewables and then use it somewhere else in another sector. This is the idea of sector coupling, in my opinion. Now, in terms of the numbers mentioned, again, probably somewhere around there. I see another question. I'm not sure if this is a new one or it's connected.
I think is a continuation of this why I put.
Okay, okay. Yes.
So
in terms of batteries, yes, indeed, it's how you see the life cycle costs several points, and sometimes yes, some studies do not take the whole life cycle of batteries when calculating, for example, the LCOE of battery energy system, or when coupled with PV and wind, they take for granted that the grid will be there. So I'm a little bit careful and hesitant when talking about costs and financial viability of different power sources, because it is largely related to how you define your study and what are your assumptions, and a different assumption can really change dramatically the final answer. Thank you for the questions. I think they are quite valuable, and we'll look into this more deeply following period.
Another question from Louise Gilles. Voila, here. So the question is not only storage capacity, it's cheap and dispatchable storage. Do you have a comparison on storage price and capacity for different storage technologies?
We do not have, as I said before, in our white paper. I do have some idea myself about storage costs and prices of battery energy storage, mainly of lower scale. But this is not really in line with this webinar. So, of course, it is not only storage capacity, it is also the question about storage power, because power is needed several times, not only capacity in an electric power system. And obviously, we want storage to be competitive, to be included into the overall energy mix.
Okay, so
Maria,
yes, indeed.
I've just copied in a link to a very interesting IRENA publication, Cost of Storage.
I'm publishing for all. So
Yeah.
if you want to,
yeah, sorry, yeah, please, yes.
Yeah, I post it, so now it's available for all. Then in the meantime, there is another statement from Mark. I go here, I copy. So I'm going to read. So there isn't enough lithium in the Earth crust to back up the electricity system on the world or the world vehicles, even without considering portable devices. There is less cobalt and even less rare earth metals, so they cannot be more than a small part of the solution.
Interesting point. I don't know, really. I cannot answer that. Could be true. But in my view, I think that when storage is the question, then there is no, as Christian usually says, there is no silver bullet. And we need different types of storage to cover the demand for storage. Either it could be at short-term storage or at large-scale storage. So if we really find out and that we cannot rely on batteries so much, then I think the market itself will regulate somehow, and other types of storage will emerge rapidly, I guess. This is a personal perspective, I would say.
Okay, thank you. Here another question from Mario Bruno Ferreira. What about the role and efficiency of power to gas approach?
Yeah,
maybe I can answer some of the questions also during the last section, because that is essentially also in the sector coupling, and we will have a round also of questions and discussions, I think, at the end, because yeah, that's a transition, I think, in the presentation now to sector coupling.
Yeah.
Okay.
Okay, let's leave that to the end? Maybe it will be answered.
Yes, I also think that it is important to listen to the whole story. I see that there are a lot of questions concerning storage, and of course there's some issues really unresolved, in particular also the cost issues. We are at the flexible generation, we are mainly talking about the technological needs, and I would like to stress out that we do not only think of the power generation itself, the electricity generation, but we have to look at also other sectors as well. And I think the next contributions by Christian gives a good overview about what we are thinking about how power generation and storage can be ideally and efficiently interlinked with each other. So Christian, please, could you continue? You have the control over the screen right now.
Thank you, Alexander, for the introduction. So thank you for the audience staying so long online. I will try to do my best to give you a short overview on the issues of sector coupling, but also the technologies of flexible generation, what the state of the art especially is in thermal power. First of all, starting with the hydrogen, because that is a hot issue discussed, if it is needed, if it is worth to go this way. Fact is, with doubling, tripling, or even going higher with wind power and PV power, the grid for the next decades will not have the capacity to bring Spanish PV power to Germany or German offshore wind power to Italy. Therefore, hydrogen is considered also as an intermediate storage, but also as a cross-sector application. And of course, with the hydrogen, we also need the infrastructure. That means we need transportation, either mixing with natural gas or in future, pure hydrogen pipelines, including the storage in caverns. And if the hydrogen is distributed, we can use it either directly for fuel cell cars, trains, or in reconversion into power and heat. We can, of course, also go into more valuable synthetic fuels, which drive aviation or shipping. And that's the last point. Once we have caverns available, which are no longer used for natural gas storage, then also hydrogen can be stored on a seasonal basis. And seasonal means something between 1 to 6 months at the end of the day, depending on the relationship between wind and PV installation in some regions of Europe. We all know that the build of new PV and wind will take 1 decade, 2 decades more before all sectors can be supplied with green hydrogen. So there is also transition technology, which is a blue hydrogen. So taking natural gas, reforming it, producing hydrogen, capturing the carbon, which we expect to play a role, at least in those countries which have a chance to store CO2. That's mainly the North Sea countries like the Netherlands, UK, and Norway. And we expect that there will be a smooth transition depending on how fast renewables are added, how fast electrolyzer capacity can be built up, that in the beginning maybe bigger amounts of blue hydrogen are available, and that then after 2025, larger electrolyzer capacity driven by renewable electricity will serve these markets. To go to the synthetic fuels, we have to consider also the need of carbon anyhow. If you want to go into synthetic kerosene for aviation or synthetic diesel or methanol for shipping, CO2 is needed. And also chemical industry purely mostly relies on the sea. That means we need, if we can go to fossil natural gas or coal, recycled CO2 or biomass CO2 to produce chemicals and fuels. In the UK and in other places also, there is the idea to create negative emissions by capturing CO2 from biomass-fired power stations and storing the CO2, which will help other industry which have less chances to fully abate the use of fossil energies. And the technology itself, the capture and also the storage underground, is proven already in many regions in the world. What you see on the right-hand side is the world's largest carbon capture plant. It is essentially a CO2 storage, but for enhanced oil recovery. So the CO2 is going underground, and on the other side of the well, more oil is recovered, but that doesn't matter. We see with 4,500 tons per day, the technology is mature enough. And now I have an issue from moving. Alexander,
yes, I will reconnect you again. Sorry. Please try it.
Yes. So what uses do we consider or does EU industry and research consider? On the one hand, of course, you always need the CO2 source and the hydrogen, and then you can go different pathways. One is the so-called power to gas. That's sometimes confusing because also people call power to hydrogen, power to gas. Second thing is power to fuel, which can be in the beginning methanol, but from methanol you can go into diesel, kerosene, or other synthetic follow-up products of methanol. And then we have synthesis of chemicals like urea, where you first go to ammonia and you take CO2, and together you have then fertilizers produced, but also all plastics and so on can be produced based on hydrogen and CO2. It's just a different route of the chemical production line, starting with another form of the sea. The technologies for reconversion of fuels, and it can be either hydrogen in future or today natural gas or liquid fuels, are well known. I just want to show the scales, what we are talking about at the moment. The largest fuel cells at the moment are in the megawatt range, but go down, of course, to the kilowatt range in cars. Gas engines are available to 10 megawatts, some 13 megawatt maximum size, and have efficiencies around 50%. The combined cycle gas turbines or gas turbine size starts in the 1-2 digit megawatt scale, but they are mostly replaced nowadays by gas engines. But then this combined cycle plants go up to bigger than 800 megawatt electric and reach efficiencies there of 63%, maybe 65% in the next 5 years. The fuel efficiency for all these technologies in combined heat and power units can be between 70 and 90%, depending on at what temperature level the heat is needed. So if it is high temperature heat for industry with steam, or if it is just a heating grid. Hydrogen is considered to replace all the fossil fuels used today in power generation, but also in power to heat applications in future. It can be directly burned in principle in gas engines, gas turbines, and fuel cells. Ammonia, on the other hand, maybe can be considered as a long distance transport molecule for the transport of hydrogen, for example, from other regions of the world into Europe, because ammonia can be more easily liquefied than hydrogen. And the splitted ammonia, which is a mixture of hydrogen and nitrogen, directly can be burned in today's machines. For the pure hydrogen combustion, there is another 5 to 10 years development needed, which is undertaken at the moment from industry. So about 30% easily can be co-combusted today, but for the 100% combustion, this development time is needed to also keep all emission limits at the combustion, for example, NOx in the combustion flue gas. The first example of a hydrogen-fired turbine will be a retrofit, which is on the way already in the Netherlands, where Vattenfall announced with its partners Equinor and Gasunie to reduce CO2 emissions by 1.3 million tons per year in 2025, when an existing plant is retrofitted then to 100% hydrogen combustion. Oops. But it's not only about hydrogen, and hydrogen is not the only solution. What is happening in the transition at the moment is that coal assets are replaced by new gas-fired investments. Like on the top, you see the replacement of a hard coal-fired power station by gas engine plants in the municipality of Kiel. On the bottom, you see previous retrofit of a coal boiler into a combined cycle plant, where a combined cycle plant was inserted in a protected building, in an existing building, to serve the whole Malmö area with district heat mainly. As said before, these technologies offer 90% fuel efficiency, and when switching from hard coal to natural gas, also already 70% CO2 reduction, and a quite flexible operation compared to the previous design. But it's not only about flexible generation, because the CHP plants on the one hand are used to supply heat to heating grids. To make them more flexible, also nowadays it's state of the art to put gigawatt scale heating storage, like hot water storage, integrated in these power plants. But the more the renewables come into the electricity grid, the more also, of course, the CHP plant suffers from the inability to reach a reasonable income from the produced electricity. And therefore, more and more also, especially in the German and Dutch context, but also in UK, projects come up adding heat pumps and electric heating into such CHP plants to avoid the production of not wanted electricity in the heat supply. That means when there's a large excess of wind or PV power, then electric heating or large heat pumps will take over. And the heat pump technology at the moment is in the situation to make a big step into the 50 to 100 megawatt range. That means commercial scale industrial heat pumps being able to support both steam to industry, but also heat to heating grids. In the past, retrofits already started 20 years ago to use existing coal-fired power plants, which are also mainly heating plants like Avedøremarkværket in Copenhagen, from coal firing into biomass firing, and the EU just has seen 3 gigawatt electric retrofits from coal-fired power plants into biomass firing over the last 20 years. On the other hand, more and more also every country in Europe looks at no longer having deposit for waste, but installing more and more waste incineration. Some countries are slow, but it's ongoing, and also that is somehow at least low carbon source of energy, so better burning the waste than getting environmental problems from deposits. And at least 50% of this biomass, of this waste also is biomass. And you see a protected building from an artist being built in the middle of Vienna, because that is important, of course, for supporting the heat directly to the heating grids, that these plants are not far outside of cities, but in the middle. That also avoids long transportation of the waste. So how does a decarbonized future can look like? The first thing what is ongoing today is optimization of all the energy systems and implementation of energy efficiency technologies. It cannot be that we still have high temperature heat going through the stack in some industry with 400, 500 degrees C. So organic Rankine cycle technology or other cycles for low temperature heat recovery are being implemented, but there's also a push needed, I would say, from policy side to give support to these projects which are directly saving CO2 emissions by using waste heat. On the other hand, also one example is the gas grids in Europe, where often the gas from high pressure up to 200 bars, in average maybe from 100 bars, is released to lower pressures without using the expansion energy. That means also such turbo expanders to use this compression energy in the gas grid should be implemented more and more. This is the low-hanging fruits and non-regret strategy anyhow. There is development for new thermodynamic cycles which allow also more efficient cycles. That is, for my understanding, a 10-year exercise. Improve also reliability and cost effectiveness of these technologies. You see on the right-hand side one example of such a pilot plant or small demonstration of such a new cycle for using CO2 instead of water as the cycle medium. We, of course, need to further improve the turbo machinery, not only for the thermal power, but also for hydropower and wind turbines, because there's always efficiency which can be gained and therefore makes the whole value chain more competitive cost-wise. And we have to develop and further deploy new technologies to capture the untapped resources of energy. That could be tidal range and current energy in the oceans, which of course have also counter effects when it comes to environment, and there also more studies have to be performed where and how these technologies can give the maximum benefit without harming environment. And same is true also for wave energy devices, which either directly in the ocean or at the coast can extract wave energy, more or less also base load. There are combinations which can be considered of fluctuating power generation and storage, like seen on the left-hand side for a huge photovoltaic plant which is integrated in a scheme with pumped storage and wind power. That enables also to make these fluctuating renewables to make them more predictable and store some of the energy for an on-demand supply. Also, areas which are not used today, like rivers and lakes, can be used for swimming or floating PV power, like shown on the right-hand side with an example from Korea. But that always depends on the regional issues, if that is a flowing river or if that is also a stormy region. That means the design of such schemes strongly depends on the natural resources and ambient condition in these areas. Fully decarbonizing the energy system means that, of course, electrification is a core step which is done at the moment and which will be further done with electric cars and battery storage, maybe at homes or in small businesses. Also, industry in small scale can directly supply themselves with wind and PV power. And of course, heat pumps are enabling efficient use not only in homes but also in small medium-sized industry, like pulp and paper industry, as one example, and now paper industry as one example, where a lot of energy is used for drying, but also waste heat is available to recover with a heat pump. It will be much more complex to decarbonize heavy vehicle transport, shipping, aviation. We will need the synthetic fuels there, especially if we talk about the big container ships, if we talk about long-range travel with planes. We will see more hydropower, maybe in some areas of Europe where still resources are there, but truly speaking, European hydropower is already very well explored, and therefore this is maybe more also something for other regions like Russia and Asia. We, on the other hand, have industry with a high energy demand, that is steel making, cement, glass industries. These industries need fuel because they work on high temperatures, and this industry most probably will go into either synthetic fuels or hydrogen directly. The hydrogen route, wherever it can be applied, is the most efficient one. Whenever you go one step further into a synthetic fuel, of course, you lose efficiency. But for the planes, which was the one example, efficiency is not the issue there. The issue is to have enough fuel on board, and not, so you need this energy density, which you have in liquid fuels. And then you see on the right-hand side also, in addition to hydrogen, of course, biomass as one more piece of the puzzle. And on the bottom, you see the seasonal storage again, which we need either based on synthetic fuels, hydrogen and biomass. But at the end of the day, there is not one technology silver bullet. We will need more of these technologies together to solve the problem. And I think that's what I wanted to say, what we wanted to say, and now the floor should be open to all questions about the presentation.
Yes, Christian, thank you. So here we have some, so let's check if there are new questions, or because there are some still related to the previous presentation, but that probably you can reply or maybe so I will continue quickly with the one that we had, and let's see if they are addressed directly to you or to Georgos from the previous presentation. So I'm here, so I copy in the chat. So this is a question from Mario Bruno Ferreira. What will be the place of DSR concerning flexibility? What will be the DSR ramping down capability? Who want to reply to these questions?
Georgios, you want to answer?
Are you referring to demand response here? I'm not sure I understood the question.
Yes, exactly. I think it's about demand response, what that can deliver. So think about aluminium industry and others which do this today already.
I think that in all the studies and the outlooks and for the future, the energy system and the integrated energy systems, both demand side management and the demand response have a role to play, and this actually depends also on the digitalization of several assets of consumption and generation. I mean, we need to have controllable loads. We need to be able to control them quickly so that we can treat after a point, the consumption as an asset more or less comparable with generation. And if we can do that, then I think it can be also a very flexible asset. I'm not sure when we will be able to do that on a large scale, though. Once we start to have more controllable loads, or more loads that can be moved in or out of the power system, then we can start thinking also maybe on a large scale. I'm talking about electric vehicles, or more and more heat pumps, or electric heating, where we can actually play with demand side management as well. If I
There's
understood
one more,
the question.
There's one more thing which I want to add. Demand comes together with all ideas about storage. So if there's a compressed air energy storage plant added, that is a demand which can be artificially, of course, increased. And if we have electrolyzer technology being installed to serve refineries and chemical plants with hydrogen as a replacement for natural gas, these electrolyzers in a millisecond can be shut down, and so give free electricity if there's more demand. And that way, I think the system will be more complex to be managed, but with increasing addition also of hydrogen technology, which we will see in the next 5 to 10 years, and also more opportunities will come up for demand side response.
Okay, thank you. Another question here from Frederic Mesuro. So what will happen if no wind or only residual wind over Europe then can happen during a weak winter with so not much PV generation? Huge storage?
That's exactly what the issue with seasonal storage via hydrogens or synthetic fuels is about. It's about a week, not a week, maybe more a month or 2 months of cold winter time in Europe, where we today get hundreds of terawatt hours of natural gas, either from Norway or from Russia. And these hundreds of terawatt hours we have to store. That means we have to extend also the cavern capacity, which we have today maybe by a factor of 2. That means we need more gas storage in future, which will be hydrogen storage at the end of the day, if we no longer can use the fossil fuels like coal or natural gas.
Thanks. Another question from Elias Altov. So, which would be the most effective measures that need to be implemented for countries with yet low shares of renewables that already face problems for the grid? What would be your advice? What would you advise those countries are the best practices that we learned about in the last 20 years?
Well, this puts into the table a lot of parameters, I would say. First of all, what types of grid issues or problems are we talking about? Are we talking about not so reliable grid that is several periods over a year without reliable electricity supply? Are we referring to something else like difficulty, like, for example, isolated grids that when we have very high percentages of renewables, then we have other type of issues? I'm not really sure, but if I can make a general comment, the low shares of renewables in some countries compared to high shares that do exist in some countries, up to now it was mainly driven by policymakers, I would say, especially starting from the previous decade, where, let's say, artificially the cost of renewables was reduced by huge incentives at several points. And this, of course, drove down at the end, eventually, the overall cost of mainly PV and wind. And now we're talking about really competitive costs with even cheaper than conventional generation. So I'm not sure I can give any advice, as the question says, but I think that if we're talking about Europe, I think eventually more or less all countries will follow the stream. Looking at the interconnected European grid, I think that going into the common markets, the electrical and energy markets also, I think it's inevitable. Okay.
Maybe one thing to add, if Europe now plans to install 4 gigawatt of electrolyzers until 2025 and 40 until 2030, which is, I would say, something which we expect from the hydrogen strategy, it would mean that 3 to 4 times more of this power will have to be installed within the next 10 years as PV and wind power, because that is the energy source to feed these electrolyzers. So massive investments will have to be done anyhow, and somehow with it, in the middle of the corona crisis, I think also people understood now that this is a good way to go, because if we invest in our European infrastructure, in our European energy production, we reduce our balance sheet and do not spend so much on imports of other fuels. So it's a win-win situation for Europe and for every country who creates jobs in these new industries. And that could help a lot, not only to come out of a health crisis, but also to come out of an economic crisis.
Thank you. I would, since we are running a bit late, like we are 15 minutes late, I would give, let's say, space to the last 2 questions, that and then I will leave the statement. Then if some of you want to reply also bilaterally or share with others. Here you find another question, so the almost last question from Mark Owitt. So here is, why does CCS analysis always ignore its risk and efficiencies? It imposes 30% efficiency penalty on the generation electrolysis. CO2 is heavier than air, so any leak at extraction, generation, or storage will form an asphyxiatic cloud that can drift over any. Just one second. Over any population center. Only strong winds will. These are unanswerable risks that cannot be legislated away, as doing so would violate the human rights to live life.
Okay, I think we are not here to discuss political issues, but one thing to mention, we only have 2 chances to go into the transition. The one way is we use a bridge, which is a fossils, and decarbonize with CCS, which is really limited in Europe to few regions where I see personally a probability that these projects may fly, with carbon capture and secure sequestration in the North Sea region. The other alternative is just now going more and more into big green schemes, but that of course also will require from oil and gas industry to quickly change the business models. So for the next 10 years, we not only talk about economy, we talk about reliable energy supply for European industry and European public. And therefore, it's a mix up of economy and politics, which we cannot clarify at all, I think, at this place.
Yeah, and I want to directly add also here to Mark. of course, we are not the policymakers. For example, when it comes to CCS, I just remind you that in Austria, for example, this is forbidden. Yeah, this is prohibited. Yeah, not each and every technology which is on the agenda of the European Union or the European Commission is agreed on. Yeah, there is no broad consensus over all these technologies. Also, to your critical remarks regarding efficiencies and about batteries, minerals, and so on, I fully agree with you. I'm a friend of pump storage, but if you look on the potentials and on the role which all these storage technology will have, I don't think we can ignore this, and every technology will have to play its role. Excess energy has to be somewhere used or stored, and the question will be how to get the energy from the summer into the winter. There will be no more coal-fired power plants perhaps in 2050. Yeah?
Yes. There was one question about this week of storage. I would guide to a more severe issue. There is a 10 years winter, which always occurs. There is one winter in 10 years, which is much colder, where we need maybe 30%, 40% more energy than in other winters. And also for that, we have to be prepared. And there is no solution on the table at the moment how to overcome this challenge until 2050 in a carbon neutral Europe.
I'd like to add that CCS, CCU might be also considered as a kind of transitional phase in Europe. This was also explained by Christian before. CCS obviously will play a certain role in the world because so there's still a large share of countries which depend on fossil fuels, and but maybe it will finally it will play only a minor role in the decarbonized Europe in 2050. So I want to stress out again that we did not evaluate the technologies in terms of which has the best chances to survive in 2050, but we gave an overview of the technologies which are actually already exist, which can be considered as a candidate for being installed in a sooner and in a rather short data time. And this could one of the ways to go into the future. And as we closed our presentation, there's no silver bullet to solve our problems for the decarbonized, also to solve to create the system for decarbonized Europe in 2050.
Okay, Alexander, tell me, if you want, we can have the space for another one, but in any case, I would like to also remind that all this discussion, all this exchange are continuing inside of ETIP SNET in our working groups, so in this case, in working group 3.
Yes.
So if some of the people that attended is not still in the working group 3 but want to join, please go on our website and send the application form, and you can continue to discuss, of course, with our expert and inside of ETIP SNET itself. So this is important to keep in mind. It's not just a one-shot spot, this webinar, and then there is no possibility to interaction with you.
Once again, maybe also it should be made clear that this is pure consultancy, that the experts somehow put together information on the toolboxes which we have and then a roadmap of further development of these technologies.
Yeah, and I would like also to invite everybody who is interested in just becoming a member of our working group to contact us. We are looking for active members, for really active members who are really willing and spending time to contribute to our discussion.
Yeah. So since I see many questions and I'm not, we cannot reply now. We are running really out of the time, and I saw also people are leaving. But I would like to ask our speakers. Maybe then we take the questions and we try to reply, and we deliver to our attendees the replies, so everyone can have their own question replied and satisfied. And again, please feel free to join the working group, as Alexander said. So more than welcome all contribution possible from experts in this field. So if Alexander, please, I leave you the closing words, and then we can close. And I want to really thank from ETIP SNET part, Secretariat, all of the speakers and all the attendees that attended this webinar today.
Yeah, so thanks a lot for everybody who joined our webinar. I will make it short because we are already over time. I would like to ask for all the very valuable questions, for the very good discussion points. We are coming back to some of the unanswered questions and give you our reply. And I would also in particular ask the three speakers to take the time to go into these very extensive stuff, because as I said, this is a contribution of 11 people who were in the task force, and we tried to collect them all and give you an overview about our activities in our working group. So you're also invited to download the documents of ETIP SNET, to go to the website. Please download also our white paper, and you are always welcome to send us your contribution, your criticism. Any feedback is fine. And I hope anyway you have enjoyed this session. And I wish you a nice afternoon, rest afternoon, and a nice evening. And yeah, I think that's it. Thanks for joining.
Yeah, and the recording will be available on the website as well, so everyone can have access to it again. Okay.
Okay.
Thank you very much. Thank you.
Thank you very much.
Thank you.
Goodbye.
Bye-bye. Are we alone?